So last time we discussed about, if you see, we discussed about Reynolds transport theorem, Euler equation, and then from Euler equation we had derived the Bernoulli equation, and after that we had discussed about streamlines and streak lines, where uh, uh, we discussed streamlines and streamlines and, or I say, stream functions and potential functions of uniform flow, then source, sink, doublet, and then flow over a body. So we had discussed last time this, and all these things are generally for inviscid flows. Inviscid means one who don't have any like for any fluid where mu is zero or dynamic viscosity is zero. But in real life, it should not, it is not like that. So just to recap of the what the Euler equation says. So from if you derive from RTT, it was in the last lecture. It says that the change of, like, this is the acceleration term, material derivative. So material derivative, that is equal to del u by del t plus u del u by del x, or I should write in the vector form, del u by del t plus divergence of u vector, or it's in the opposite way, u vector dot divergence into u vector. So this is what this material derivative means, and I explained that this is temporal term and this is convective term, and this is equal to pressure gradient. So this is pressure gradient plus, it should be multiplied with rho, plus rho into some, this is what is body forces look like. So this is temporal term, this is convective term, this is pressure gradient, and this is body force. So all things is in vector form. So if you like write in Cartesian coordinate x momentum, then this u will be written by u, which is scalar. So rho del u by del t plus u del u by del x plus v del u by del y plus w del u by del z is equal to minus dp by dx plus rho into xi. So xi is the component of the body force in the x direction. Similarly, for y momentum, the same equation will go. It is like rho del v by del t plus u del v by del x plus v del v by del y plus w del v by del z is equal to minus del p by del y plus rho xy. Similarly, for z momentum, it is like that. Rho into some components of v will be replaced by w is equal to minus del p by del z plus rho xz. So in each term, this is the temporal term, this is the convective term, this is what is called the pressure gradient, and this is the body force. Now, we will solve some equations, like some questions related to Euler equation. So the basic assumptions is this is for the inviscid flows. It don't Euler equations that don't have this viscosity term. That's why the only force that is coming because of motion is the pressure gradient. If it has a viscosity, then the shear stress will also act, and that will lead to an equation that is normally called as a Navier-Stokes equation. Okay, so we will solve some equations. So one question is this: from the Euler equation only, we assume that the flow is just inviscid, or we will use this equation. And our thing is like, suppose I'm saying that this is the like, if you say this is your control volume, okay, and where this is the inlet and this is the outlet. And we need to find out how much force should be required to hold this wall. Okay, this is a like a simple question. So if I just draw the control volume, what it looks like, so it is something like that. And the assumption is it is the inviscid flow. So this is what. So here is the inlet. Here is from here and here is the outlet. Now the diameter of the jet is 10 centimeter and Vj is equal to 8 meter per second. So if we just take this thing, what is the mass flow rate that is coming? If I'm seeing that this is water, so I should find what is the volume flow rate first. So volume flow rate is equal to pi by 4 d square into Vj. So if you solve this, it is 8.14 into 0.25 d square is 0.1062 into 8. So the volume flow rate is 0.628 meter cube per second. This is the volume that is coming in. Now, if you apply, first the assumption is it is steady and incompressible fluid, I should say flow. Then, if you write like this is x direction, this is y direction, so x momentum equation will come as um, so if I write it is sigma of fx is equal to du by dt. This is in x direction. So all the summation of all forces is equal to what is the material derivative of velocity, that is equal to del u by del t plus u del u by del x plus v del u by del y plus w del u by del z. And so this is like in this is this equation is in differential form, and if you write in the integral form, it is sigma of fx is equal to del of del t of, this is rho rho u dv plus this is equal to rho u v dot n cap dA. So this term is like this, and all this term is like this. So this is in the integral form. So we will use the integral form here. So first we say that this is a steady state, so this term will be 0, and we will try to use these equations to select. Suppose this wall is exerting a force of F on this control volume. So this is your control volume. So if the wall is exerting a force on the control volume and everywhere the pressure is pre-atmospheric, pre-atmospheric here also, this place also, and this place also. So just rewriting this equation. So first rewriting this equation, if you say here the velocity is coming in x direction, but there is no exit in the x direction. So this term will be rho u. So u is like ui cap because it's coming in this direction, right side in the positive x direction. Now v dot n cap is the area of this sector is in this direction. This is minus I cap. So if I'm saying this n cap, the normal vector to this area is minus I cap. So v into I cap into minus I cap, and this into area. So this is what the expression for this for the inlet, and there is no outlet, so outlet term will be 0. So just if you simply say, it will be rho u minus rho u v into a. Now rho v into a So it is minus rho q into the velocity. So this is like coming from this side. Now all the summation of all forces equal to this. Now if I say suppose this is the force that is acting on the control volume, it is minus F plus the atmospheric pressure is P1. So it is so P atmospheric. So the force on the control volume is P atmospheric. It should be in gauge pressure. So I should write in this way. Suppose it is P, which will be later equal to P atmospheric. So it is P minus P atmospheric into area is equal to, so this is equal to minus rho A u square, or we can say also rho q u. So it is minus. Now, if we simply solve, so I am saying that P is equal to P atmosphere. Everything is the atmospheric pressure. So this term will go to 0. So minus P is equal to minus rho q u, or rho A v square or u square in the negative direction. So this is the force that is acting. It is rho A v square. So force on the control volume is rho A v square. So you know A, what is V. If you assume that its water density is 1000, you can calculate what is the force. So this is the force that is acting on the control volume. Now the same force will be applied on the wall. So if I draw the free body diagram of the wall, because of Newton's third law, this same force will be applied on the wall. And if you want to hold this, you need to apply the same force. So that is what equal to F. Hence, this same force, because of Newton's third law, this control volume will apply on the wall, and you need to apply this F force to hold the wall stationary. Therefore, F is equal to rho A V square. This is F0. So, in this way, this question will be solved. Now, there's a slight change in the question. So here what happens if you say sigma of Fy component, here the exit from both the sides are equal, and since exits from both the sides are equal, the sigma of Fy is equal to 0. Therefore, we are not bothering about the Y exit of the or the outlet of this jet. Now what we will do is, we have this system. If you see, here the inlet is like this, and water is coming in this way and going and passing through this. Now again, what is the force that is required to hold this setup? Now the slight change is, if you see here, there is an outlet that is also coming in X direction. So what we will do is, so suppose sigma. So I'm saying that this is my control volume. So why this force is coming? Because there is a change in the direction of the velocity that will induce acceleration, and hence the force will come. Okay. So this is what is the flow channel, and I'm saying that this is the force that is applied on the control volume. So this is my control volume, and everything is P atmospheric. So so this is your X direction, this is your Y direction. So if I apply sigma Fx, that is equal to, what is the velocity here? Velocity is in this direction, and area vector is in minus I cap direction. Here velocity is in this direction, and area vector is also in this direction. So we will try to write, so inlet F efflux is equal to, so it is, if you say, it is integral of rho u v dot n cap dA, that is equal to, so if you say, it will be rho u would be u I cap, then v dot n cap. V is in u I cap direction and area is in minus I cap, because if you see, the area is For this perpendicular area, the area vector is minus I cap direction. Okay, into what is that is called the area. So, if I say it is rho u square a into minus. Now, what is the outlet efflux of momentum? So that is equal to rho u same v dot n cap into dA. Now here what you will see, if you will see that rho is there, velocity is u I cap but in negative direction. Okay, u I cap. Also, similarly, the velocity is u I cap but is in negative direction dot minus I cap into area. So it will come as, so this minus and this minus will turn out to be plus. I cap into dot I cap is 1. So it is minus rho u square a. That is I cap because it is in x direction. Therefore, sigma of fx is equal to minus 2 rho u square a. Now, this sigma of fx is equal to minus h0. That is the force acting on the control volume plus P minus P atmospheric into area. So whatever be the force that is acting on the control volume will always be the gauge pressure. Minus 2 rho u square a. So if my pressure is everywhere is atmospheric, this term will be P atmospheric and whole term will go to 0. Therefore, minus S0 is equal to minus 2 rho u square a. This is equal to S0 is equal to 2 rho u square a. Now this is the force that is acting on the control volume. Now in the for the if you write for the like whatever be the part, these same force will applied on this part F0 and to hold this you need to apply this force. So this is the force that is applied and the direction in the leftward direction you need to apply. So this is the force that is on the control volume. Now control volume exert force in right hand side direction, and again you need to apply in left hand side direction. So in this way this problem is solved. Now here what you will see, here for sigma of y fy you will see that there is no any other component. If we say that the weight diameter is very small, that is the weight of the liquid in this column is very small, so then it is sigma of fy is almost equal to 0. Here, if you see, the exit is in some angle with the horizontal. It is not exactly like in the earlier case perpendicular or parallel. So what happens is there will be a component. So to handle the component, we will try to see how to solve this question. So if I'm saying that, so this is my control volume, that is, and there is some force that is acted by the wall to the control volume. So this is like this, and the exit is like in this way and in this way, and this is 30 degree and this is 30 degree. Now the area here is A1, the area here is A2. The first thing is A1 is equal A2 is equal to half of A1. This is the first thing that is given. So if you do this, the velocity in V1 is equal to velocity in V2 because it is split in two parts. So V1 is equal to V2 and here also V3. Okay. So another thing is A2 is equal to A3. Now what we will do is we will try to find the components of velocity. So if you say this is V3, so this is V3 cos 30 and this is V3 sin 30. Similarly for here, V2 cos 30, and this is V2 sin 30. So simply just breaking the components of velocity. Now applying this same Euler equation, sigma of fx is equal to, so what is the, like if I say this is my inlet and this is my outlet, so this is the direction, the x direction, and this is in y direction, that is equal to, first, what is the influx? I should write it. Inlet efflux, that is equal to rho a v square or u square. So I should write it as v square, rho a v square. Now, what is the outlet? Outlet flux, that is equal to, so if you write it is rho into v, and it is v dot n cap dA. So if I say that it is rho into v cos 30 or v2 cos 30 into v dot n cap is, so like if you say this is your n cap direction and your velocity is in this direction, we are resolving in this direction. So it will be just simply go up with, so suppose this is your I cap and we are, uh, or I should say my, this is I cap and this component, this direction is I by cos 30. So in this way we can say, so simply it will be V2 cos 30 into, that is also in negative I cap, and this is also in negative I cap divided by cos 30 into area. So it is rho V2 cos 30 into V2 into area. So this is equal to rho V2 square area into cos 30. Now what happens is, because there are two components, we will try to add up these two components. So it is equal to, so if I say 2 times, so it will be rho q v2 cos 30 minus v1 is equal to minus f0. So minus f0 is equal to rho into q. So it is rho into v2 cos 30 is, so if you say cos 30 is root 3 by 2 into v2 minus v1, and we know v2 is equal to v1, so it is rho q. So it is something like that, rho q into root 3 minus 1 by 2 into v1. So this is what is the force that is acting on the vane. So in this way you can solve the question. Now we will try to look at, so this all the theories has been derived for inviscid flows, but in real life all all the things have the viscosity, and the viscosity will create a shear stress. So in the first Newton's law of viscosity, we said that the shear stress is proportional to rate of deformation. Shear rate of deformation was equal to mu du by dy. So when there is a flow and there is a there is a viscosity, there is a shear stress, and we don't encounter that in the equation. So now we will look into the Euler equation. So the thing that will change is, so suppose this is your control volume, and this is something that we called earlier as a pressure force that is acting perpendicular to the area of control volume. Or but in this case, we also have the shear stress that is acting parallel to the surface, and this is what we called as this is called as what is tau ij, and it is called tau ij because this notation indicates like whatever the whatever be the plane or normal to the plane where it is acting, normal to the plane where it is acting, and this indicates the direction. So suppose in Cartesian coordinate system, if you say, so this is my Cartesian coordinate system. Drawing only x direction and y direction. Okay, this is your x and y direction. So what happens is, uh, this is tau 1 1. Why 1? So this area has a normal. So this plane has a normal in x direction. So it indicates in x direction, that is 1. So x is represented by 1 and y represented by 2. And the second thing, so if I tau 1 1. So this represents the plane normal. So that is in x direction. And second is the direction of this force. So direction of this force or this stress is also in x direction. Now in the similarly, if I draw in this way, what will represent this? So this is the direction of the force. So if it's in this way, it is tau 1 2, because the normal to this area is in the x direction, but it is acting in the y direction. Similarly, for this, if you draw in this way, it is tau 1 1. If you draw in this way, it is tau 2 2. Here also it is tau 2 2. Now for this, if I draw, what it equals to? Tau 2 1. Why 2 1? Because 2 indicates it is the area is in y direction, and 1 indicates that this is parallel to x axis. Okay. So in this way it is represented, and it is this tau ij is is called second order tensor. Second order tensor. So we all know that scalar doesn't require any direction. So scalar doesn't require any direction. Now vector require one direction. So vector require magnitude and direction. But so vector is, so if in terms of tensor we derive, so scalar is zero order tensor. Vector is the first order tensor, and just here we discussed whatever the shear stress, it is second order tensor, because it requires magnitude as well as two directions, the surface on which it is acting as well as the normal to the, like, what is the direction. So it requires two directions. So this is what is we call as shear stress. So if we simply apply and solve in the Navier-Stokes equation, sorry, applying the RTT. So what RTT says, for any n extensive property, let n be any extensive property, and small n be any intensive property. That is means small n is equal to capital N by M. Therefore, if I say I have two forces, one forces is control surface tau ij dot n cap dA. This is the this is the surface force because of shear stress, plus rho into x vector dot dv. So this is the body force. So if I say this is surface force, this is body force, that is equal to rate of change of, uh, so I should just a second. First I should write what is, Yeah, first up, let me write the RTT. So what RTT says that dn by dt for any system that is equal to rate of change of for any control volume rho and dv plus control surface rho and v dot n cap dA. Okay, so this is what RTT says. So this is the rate of change of summation of all forces that is equal to surface force plus body force. If I am writing for momentum, okay, then it is like that. That is equal to d of dt of rho v dv. This is for the control volume plus control surface rho v v dot n cap into dA. So if you say this is what is the temporal term and this is what is the convective term. And in the left hand side, apart from if you see the Euler equation, this term was already there, but another term that has came that is the surface force. And surface force that is related to shear stress. So if I just use a Gauss divergence theorem at this point, so it is should write it as tau I dot n cap dA. If I use a Gauss divergence theorem at this point, it is control volume of this Gauss like divergence of into dV, and this term is like the same for the control volume rho x dV. This term remains the same because in the control volume rho v dV, and this term will change, and this term will change as divergence of rho u rho uv into dV. So this is for the control volume. So simply if I write all the equations, and because everywhere it is dV, so we can take the integration into the system and equal to 0, you will get del v vector, or I should write in row del v or ui vector. So it I can be in I cap or j cap or k cap plus v dot n cap, sorry, into ui is equal to rho into xi. So this is in the I cap direction plus del tau ij divided by xj. So what it means is I is the direction and j is the value that can change from 1 to 3. So it can be 1 to 3. So it's just a gradient. In I cap mean this can be explained as tau 1 1, tau 2 2, tau 3 2 3, tau 2 1 2. So if I write this tau 1 1 form in the three-dimensional, you will see that it is like that tau 1 1, tau 1 2, tau 1 3, tau 2 1, tau 2 2, tau 2 2 3, 3 1, 3 2, and 3 3. So this what is called as a uh, stress matrix. Okay, this is called as matrix. So this is a general form for any like for any fluid. If you see, we have 9 components. So total unknowns now we have u, v, w, three velocity components. Then we have three unknowns, and we have 9 unknowns in shear stress. So we have total 12 unknowns, and we have only 4 equations, that is continuity, x momentum, y momentum, and z momentum. So only 4 equations. So as you know, you cannot solve any problem if your number of equations is equal to number of unknowns. If that is not equal, you cannot solve the equations. Now what we will do, because we have only continuity, x momentum, y momentum, z momentum, then we will use what is called a constitutive relationships. Constitutive relationships or constitutive equations. And we will try to reduce the number of unknowns, and we will try to for example, your Fourier law heat conduction is a constitutive relationship. So we will try to use and simplify the equation. So for this Navier-Stokes, the one assumption that will be there. So if there is no any body couple, so what they say is the shear force that is acting tau 1 2 will be, so suppose here it is tau 2 1, it is tau 1 2, it is tau 2 1. So they say that no body couple is acting. So if so suppose this is the moment. So sigma of all moment is equal to 0. That means if there is no any body couple, so whatever shear stress acting, whatever with a couple it is, if suppose this is dx and this is dy, so tau 1 2 into dx, so this is force into perpendicular distance is equal to tau 2 1 into dy, and the area perpendicular to is dy into dx. So this is the moment acting in the clockwise direction or counterclockwise direction, and this is the moment acting in clockwise direction. So this means equal to tau 1 2 is equal to tau 2 1. Hence, number of equations has reduced. So this term are equal, and if I say tau 1, this one term and this term are equal, and this term and this term are equal. So tau 1 2 is equal to tau 2 1, tau 3 2 is equal to tau 2 3, and tau 3 1 is equal to tau 1 3. So now we have total, we have reduced the equation to 10 unknowns and only 4 equations. So we had reduced somewhat, but it is not reduced as number of we wanted. So 3, 4, 5, 6, 7, 8, 9, 10. So actually it is 9 equations, 9 unknowns and 4 equations. So now what we will do is we will try to develop this shear stress part. We say tau ij. We apply the assumption of Newtonian fluid. So assumption that will come is Newtonian fluid, and Newtonian fluid says that shear stress is directly proportional to velocity gradient. And if you apply these equations and solve the equation, then uh, your equation will turn out to be, I would say, 5 unknowns. And then again, this is a Newtonian fluid, and the second, so Newtonian fluid, and again this is assumption. Uh, this is also assumption, and then we will apply one more assumption, what we called as Stokes hypothesis. Stokes hypothesis, and then finally you will come to, finally the equation that comes is Navier-Stokes equation. So, like it's a very long derivation. If you have time, you can see. But like the assumptions that came is, it's first, the assumption here also is non-deformable control volume. So non-deformable control volume, no body couple, then Newtonian fluid, and then Stokes hypothesis. So the Navier-Stokes equation that you get is, so after writing Navier-Stokes, it will be like Navier-Stokes equation. It is rho du vector divided by dt. So this is your acceleration term is equal to minus del p by del s plus mu del square. I should write in vector form, minus this grad p plus del square v plus rho x vector. So this is a material derivative and you just split it. It is like del u by del t plus v dot gradient into u vector. This is the same the pressure gradient term minus del p by del s, del p by del y and del p by del z. This term is what is called as a diffusion term. Diffusion term. And it says that your viscosity is diffusing or changing the velocity. That is equal to mu del 2, if I say u by del x square plus del 2 u by del y square plus del 2 u by del z square. So this is in x direction. Similarly, for y direction, it is v, and for the all the components, and it is mu del 2 w by del x square plus del 2 w by del y square plus del 2 w by del z square. And this is the body force. So this is the diffusion term. This is the pressure gradient. This is we called as a body force, and this is what is called temporal term, and this is what is called convective term. Okay. Now we will try to the so what is the like if you if you see it is second order non-linear partial differential equation. So second order non-linear because second order is coming from this term diffusion term, and non-linear is coming from this term convective term. So in the Navier-Stokes equation, if someone say what is second order bringing here, so which components you say diffusion term. So diffusion term has a second order, and what brings the non-linearity in the equation? It is convective term. Why convective term? Because it is u into del u by del x. So if the same component is multiplied with same unknown is multiplied together, it is called a non-linear term. Okay. Now what we will do is we will try to solve simple examples using the Navier-Stokes equation. So suppose you have flow in between parallel plates. So this is uh, y equal to 0, y equal to h by 2, y equal to minus h by 2. So we call this as a plane Poiseuille flow. Plane Poiseuille flow. Okay, so this is plane Poiseuille flow. Now what happens is this is your flow that is happening. Now you will write that as, if I write all the equations, and the assumption here is flow is incompressible, steady, and yeah, okay, and no any body force. Okay, so if I just say I should write all the equations. So continuity equation for incompressible flow is, yeah, it's a two-dimensional flow. Two-dimensional flow. The flow is happening in x and y direction only. Del u by del x plus del v by del y is equal to 0. Then the x momentum is del u by del t plus u del u by del x plus u del v by del y is equal to minus dp by dx plus mu del 2 u by del x square plus del 2 u by del y square. This is your x momentum, and your y momentum is rho del v by del t plus u del v by del x plus v del v by del y, that is equal to minus del p by del y plus mu del 2 v by del s square plus del 2 v by del y square. Now we will try to solve this equation. So if I say the flow is incompressible, first this is the content equation that will come. If the flow is steady, we say that del u by del x is equal to 0. That means the flow has fully developed, or sorry, I should write in this. Del of del t is equal to 0. This is the meaning of steady. Okay. Now another concept is we need to write another assumption is flow is fully developed. If flow is fully developed, so it means that there is no change of velocity in the s direction. Well, the flow has already been established. This is the meaning of fully developed. Okay. So for every y, the flow has fully developed. Now, if I just put the assumptions into the equation, so this term will be equal to 0, this term will be equal to 0, this term will be equal to 0, this will go away, and again this term y also, because steady state, then the fully developed. So okay, now all these are the terms that has gone. Now another assumption, if you say del u del x is equal to 0, that means del u by del y is equal to 0 from the continuity equation. That means y is not, v is not a function of y. V is not a function of y. So whatever be the velocity of v here, it should be equal to here. Here all have the same velocity. For common x, for common x, v should be constant because it's not a function of y. That means whatever v is here, that is equal to here, here, and here. Hence, because these are the walls, there is no any velocity component in this direction. That means v is equal to 0 for everywhere. Okay. Now, since v is equal to 0, so this term will also go to 0. This term will also go to 0. This term will go to 0. This term, and this term. So here, if you see, you will get that pressure is not a function of y. So pressure is only function of x. So this partial derivative will change to a ordinary derivative, dp by dx. So what is left? So left is dp by dx is equal to mu d2u by dy square. So it's a simple OD, ordinary differential equation. And if you see, this is a function of x, and this is a function of y. So this can only be possible if both each a and b are constant, because one thing is a function of x, one thing is a function of y. Therefore, if you solve, u is equal to 1 by 2 mu. If you just integrate dp by dx into h square, sorry, y square plus c1y plus c2. Now we have two constants, so we need two boundary conditions. So one boundary condition is at y is equal to minus h by 2, u is equal to 0. That means at this point, you have a no slip boundary condition. No slip boundary condition, and similarly for this point also, no slip boundary condition. So second assumption is at y is equal to plus h by 2, u is equal to 0. So if you just simply solve these two equations, another boundary condition that can be possible because it is symmetric, at y is equal to 0, du by dy is equal to 0. Because it's symmetric, if there is a velocity 0 here and velocity 0 here, it will go like this, and at this point your du by dy is 0, gradient of velocity is 0. So if you simply just solve this, you will get the constants c1 and c2. So let me solve this thing. So if I say y equal to 0, if we take gradient, here is y, but this component is not there. So the first thing that is come is c1 is equal to 0. Now the second thing is, if I say at y is equal to h by 2, u is equal to 0. So if I put that thing, 0 is equal to 1 by 2 mu dp by dx into h square by 4. So plus C2. So C2 comes as minus 1 by 8 mu dp by dx into h square. So simply if I put in the velocity profile, it is 1 by 2 mu dp by dx h square by 4 minus y square. So this is the equations that we get. So yeah, this will be negative. Now we have the velocity profile. We can find the volume flow rate. So suppose uh, this is your channel, and this is your height h. And if I say the perpendicular to this direction is some quantity v, so what is the area that is flowing? Area is equal to b into h. Now what is the total volume flow rate? So total volume flow rate is u into b into h. But since u is varying in the h direction, you need to integrate this term. So what happens is, you need to write in this way. Suppose you take this elemental strip, okay? You will say that u into b into dy into rho, and it is minus h by 2, 2 plus h by 2. So this is the total mass that is flowing, and this mass is equal to, this is the total mass that is flowing, and this is equal to rho a into u bar. So this is mean velocity. So if I just take this term out, u bar is equal to 1 by a. So area is b into h, so 1 by b into h, and again b is constant, so it will come out of the integration, minus h by 2 to plus h by 2 u into dy. So this term will go away. It is 1 by h minus h by 2 to h by 2 u into dy. So this is the mean velocity. So if you just integrate it, it will be minus 1 by 2 mu dp by dx into 1 by h, and it is h square by 4 into y, and minus y cube by 3, and the limit is minus h by 2 to h by 2. So it is minus 1 by 2 mu dp by dx into 1 by h, and this is equal to h cube by 8 minus um, h cube by 24. Again it is minus, so this will be plus, again h cube by 8. So this is minus, 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 plus, and again this is minus plus h cube by 24. So if you solve this thing, you will get the average velocity component. And what is the maximum velocity? So maximum velocity is, if you just simply use the maximum minima concept for the maxima or minima, du by dy is equal to 0. If you make that thing to happen, it will be 2y is equal to h square. Uh, so if you simply solve, you will get, if you make it derivative, you will get what, where y maximum will occur, and you will get y maximum will occur, and also you will get what is the u max. So you will simply get u bar is equal to, or 3 by 2 of u bar is equal to u maximum. That means u max is equal to 3 by 2 of u bar, or you will get some relation. You can try on its own. Now this is the plain Poiseuille flow. The second condition is, what happens if the top surface has a velocity instead of the pressure gradient? So here we say that it's the pressure gradient that is driving the flow. Now we don't have pressure gradient, we have the velocity that is driving the flow. That means the only term that is earlier, if you see it, it was there. So this term is not there. So simply u is equal to C1y plus C2. So if I say this is y equal to 0, y equal to minus h by 2, y equal to plus h by 2. Now at y equal to 0, du by dy, no, we cannot apply this. At y equal to, because it's not a symmetric boundary condition, here we have a plate velocity, here it is 0. So at y is equal to minus h by 2, u is equal to 0 because of no slip boundary condition. At y is equal to plus h by 2, we have u is equal to u naught. So I'm saying that this is u naught because also of no slip and the plate is moving relative to it. So if you just simply put y equal to h by 2 on and this, so minus h by 2, it is 0. So C1 into minus h by 2 plus C2 is equal to 0. Now second boundary condition is u naught is equal to C1 into h by 2 plus C2. Now if you say here it is C1 into h by 2 is equal to C2 simply from here, and if you put here u naught is equal to it is 2 C1 or it is C1 into h, or C1 is equal to u naught by h, and simply if you just put C2 is equal to, so it is the C1, so it is u naught by h into h by 2, so it is u naught by 2. So your velocity is u is equal to u0 by h into y plus u0 by 2. Okay, so this is your like velocity component. So if you write u by u0, it is 1 by 2, or I should, let me check whether everything is minus, this is plus, is equal to, yes, half plus y by h. So this is the velocity profile in this direction. So you can see that this is a linear velocity profile. So here the velocity profile is like this. Now for pressure gradient, like in the pressure gradient we said, when we have only pressure gradient, the velocity profile is was uh, like that, and here and at the center we have maximum, and it is like this. Now when there is a what we say wet flow, when the top is moving, we have a velocity profile like this from the center, and at the top we have a maximum velocity, u is equal to u0. Now if we have a flow where both the things has combined, then what will happen? For that, at different pressure gradients, you will find out that first this will be there. Okay, this is for dp by dx is equal to 0. Then it will be like this if the pressure gradient is favorable. So, and again, this all part is dp by dx is less than 0, or the flow is driving the flow. What is the meaning of dp by dx less than 0? So in the pipe, here it is a higher pressure gradient, and here it is low pressure gradient. So what happens is this pressure gradient is driving the flow. Now at this point, we also have a condition of dp by dx greater than 0. At such case, what happens is it is like this. Okay, and this is called, and if you just simply take this line, this is called the flow reversal. So at this point, the flow is reversing, and also at this point, the flow is reversing. So this is what is called a flow reversal. So if you just so at some dp by dx, you will also find that the flow pattern is like this. if you say it is like this, or I should say it is, let me draw it again. It is, this is was the linear velocity profile. Let me draw it again. So, so it was like this earlier. Now, at some point, you will find that your like this profile would be like this, and average volume flow rate through the section is zero. That means whatever flow is happening at this direction, the same flow is happening at this direction, in this direction. So what happens is you will get a net no flow in the channel, and the flow is reversing in this circular pattern. So for that, what you need to do is only q dot is equal to minus h by 2 to h by 2 u dy is equal to 0. If you solve this equation, you will get what you will get a pressure gradient that should be there so that no flow should take place and only a flow reversal will happen. So you can solve that thing and you can get what is we call as a flow reversal. So let me give you some hint if that is possible. Yes. So if I say so, so suppose you have okay another part. Now this is like a only single fluid is flowing in this channel, only single fluid. Now what happens if this is like another condition? So another question is what happens if in the channel you have two fluids? So suppose in it is like this. This is uh, fluid one, and this is your fluid two. So this is your fluid two, and this is your fluid one. So this fluid has a mu. It is mu1 dynamic viscosity density rho1. This fluid has mu2 and then density is rho2. Now how we can solve this equation? So if you say that it is a plain positive flow, it is not a quiet flow. That means it is driven by only pressure gradient. So what will happen? So again the no slip boundary condition will be there. So suppose this is, I am saying it is y equal to 0. This is y equal to h. So this is y equal to h. This is y equal to 0. Here the because of no slip, the v is equal to u is equal to 0, and here u is also equal to 0 because of a no slip boundary condition. Now we need to solve Navier-Stokes equation for fluid 1 and fluid 2 separately. So that means for fluid 1 we have a Navier-Stokes equation. For fluid 2 we have Navier-Stokes equation. That means dp by dx is equal to me mu del 2 u by del y square, and here also it is dp by dx is equal to mu del 2 u by del y square. That means we need two boundary condition for this term and we need two boundary condition for this term. But we have only two boundary condition. We don't have four boundary conditions. So we need to in what we say induce or generate two boundary conditions that we are not seeing, but it is there. So let me put margin. So for fluid 1, for fluid 2. So u is equal to 1 by 2 mu dp by dx into y square plus c1y plus c2. Similarly, u is equal to 1 by 2 mu dp by dx. So it is mu1, it is mu2 into y square plus c1y plus c2. Now the first boundary condition is at y equal to 0, u equal to 0. So that means c2 is equal to 0. We can just put y equal to 0. That means c2 is equal to 0. Here at y is equal to h, your u is equal to 0. So simply if you put c2 plus c1h plus 1 by 2 mu 2 dp by dx into h square is equal to 0. Now we get here c2 is equal to 0. We get one relationship between c1 and c2. Now it is not a completely solved question because here c1 is unknown and here c2 and c1 are dependent on each other. The next boundary condition that will come is at this interface u of fluid 1 is equal to u of fluid 2. So that means u of fluid 1 is equal to u of fluid 2. There is a continuity of velocity at this point. Okay. So this is what is called one that we will use one boundary condition. The another boundary condition that will come is at the interface. So suppose this is the interface. If suppose this fluid is exerting pressure at this direction and this fluid is exerting like not pressure, we say shear stress. So this should be equal. If that is not equal, then the flow would be accelerating. Since the flow is fully developed, this term should be equal to this term. That means uh, tau at the interface is for fluid 1 is equal to tau at the interface for fluid 2. Or that is means u1 du by dy of fluid 1 is equal to mu2 du by dy of fluid 2. So now we have four boundary conditions and we have four unknowns. We can simply solve this problem and we can get the equations. Like what is the equation for velocity profile? Okay, that will be in function of y and that will incorporate both the fluid layers. So in this way, we can solve the problem. Now, this is what is in a closed channel. Suppose what happens is, I would say you have a flow at this plane where the flow is happening, a thin film of flow is happening, that is inclined, and everywhere P is a P atmospheric, and this is at some angle theta, and you need to solve. So this is some thin film of height h, and the gravity is acting, and you need to solve velocity profile. You need to solve for what is the velocity profile. So this is like another example of this question of solving the Navier-Stokes equation. So if you see these equations can be what you say can be reduced to a ordinary differential equation, a linear ordinary differential equation where exact solution is possible. This cannot be possible every time, but here also you will see. So how we solve this question? Because we have a gravity, we have an inclined plate, and the thin film is flowing. We need to find what is the velocity profile over this thin film. So what we can do is just illustration of a simple concept that I will take two planes. This is my x direction and this is my y direction. I will not take a ordinary plane. I will transform this to inclined plane. Now I will try to. So this is your theta angle. So again this will be your theta angle. So if I say okay, so this is theta. This is 90. This is again 90 minus theta. So this is 90 minus theta. Okay. So here it is theta. So it is g cos theta and this is g sin theta. So along the plane we have a g sin theta component and perpendicular to the plane we have a g cos theta component. Now we resolve the gravity term. So we will write the first what you say continuity equation. This is the continuity equation for incompressible flow and assumption is same incompressible, fully developed, steady state. Okay. So this is what is now x momentum is del u by del s plus rho u del u by del s plus v del u by del y, that is equal to minus del p by del s plus mu del 2 u by del x square plus del 2 u by del y square. Now we have a x, in the x direction we have a gravity component, so it is rho into g sin theta. This is x momentum. Now we will have a y momentum. So what y momentum says? Rho del v by del t plus u del v by del x plus v del v by del y is equal to minus del p by del y plus mu del 2 v by del x square plus del 2 v by del y square minus rho g cos theta because it's in the negative y direction. Now, first from the fully developed condition, you have del u by del x equal to 0. That means this is equal to 0. That means v is not a function of y, and since this is a plate, we can say that v is equal to 0 for every x. So first thing that is coming is like this. Second thing is a steady state. So for a steady state, this term will go to 0, this term will go to 0. So fully developed, this is equal to 0. This here v is 0, so it is 0. V is 0, so everything is like here go to 0, and this term is 0. Now, if you see, you will get something like this. In the y momentum equation, earlier we don't have anything. If you see in the y momentum equation at this point, you don't have anything at this point. Now, but here, if you see, we have something like dp by dy is equal to minus rho g cos theta. So that means if I say y momentum only, that means minus del p by del y is equal to rho g cos theta, or p is equal to rho g cos theta into y plus some function of x. Because we are only integrating with respect to y, there can be some function of x that can be there. Now, another condition is this is atmospheric condition. That means at y is equal to h, p is equal to p atmospheric. So p atmospheric is equal to rho g cos theta into h plus some function of s. But if you see for every x, you have the same pressure. That means it can be possible because if you say for every x the pressure is same, this can be possible only when this term is equal to 0. Hence, the your only when I should say not this term equal to 0. This can be possible only when this is a constant and not a function of x. So your C is equal to PATM minus rho g cos theta into h. So simply putting the C value, that is your Fx, P is equal to rho g cos theta into y minus rho g cos theta into h plus PATM. Okay. So it is like this. Now, another thing. So this is your x momentum. You will get a pressure from y momentum. You will get a pressure gradient. Now, in the x momentum, if you see, That means mu del 2 u by del y square is equal to minus rho g sine theta. Okay. And if you solve this, you will get u is equal to 1 by rho mu into g sine theta into y square by 2 plus c1y plus c2. Now, what happens is you need two boundary condition for velocity, and the one boundary condition is no slip boundary condition at this point. But we don't know the second boundary condition. The second boundary condition is if suppose there is air, what happens is we will induce the shear continuity of shear stress, and it says that well mu of liquid into du of dy of liquid equal to mu of air into du by dy of air. So if I say that mu of air is much less than mu of liquid, we can simply drop this term and that is equal to 0, or du by dy of liquid is equal to 0. This is the second boundary condition that will come and we can solve the velocity profile. So here we have C1 and C2 that can be solved from no-slip boundary condition as well as du by of dy is equal to 0. So you can simply solve this equation. Like this is exact solution of Navier-Stokes equation because we are dropping off the convective term. That's why it is possible to get the exact solution of Navier-Stokes equation. Now, suppose if I say there is a now suppose if I say you have a very large tank and uh, so you have a very large tank and you have a plate, okay, and you just move this plate with a velocity of u. You just slide this plate with a velocity of u. Now this is a fluid, so very large fluid. So this height is so this is y, this is x. Now you need to solve this equation. So like suppose again I should write the continuity equation del u by del x plus del v by del y is equal to 0. It is 2D incompressible flow, but it is not a steady state problem because I will explain you why. X momentum del u by del t of rho plus u del u by del x plus del v by del y is equal to minus del v by del x plus del u by del y square rho del v by del t plus u del v by del x plus v del v by del y is equal to minus del v by del y plus mu del 2 u by del x square plus del 2 u by del x square. Now, since the initially the fluid is stationary and only the perturbation happens because of this sliding of a plate, hence we can say that there is no any pressure gradient that exists. The second thing is since all the points of the plate is moving at a constant velocity, hence we can say that there is no any gradient of velocity at in the x direction. That means this term will be equal to 0. Hence, this term equal to 0. And if we apply no penetration condition at this point, it is v equal to 0 for every y, for every x. So this term will equal to 0. Okay. Now, since du by d is equal to 0, this term is equal to 0. This term is equal to 0. This term is equal to 0. So if you simply say you will get rho du by dt is equal to mu d2u by dy square. So what happens is, if you simply see this term, there is In the earlier case, we don't have a time term. What we say, we have only the we assume that it's a steady state problem. But from your intuition or your common knowledge, if you slide a plate at t is equal to 1 second, suppose this velocity is felt by only this point. At t is equal to 2 seconds, this velocity is felt at this point. So with time, this x is evolving. So it is not a you say steady state problem because the x is changing with time. Now how we solve this because it's a time term, it's a space term. So your u is a function of time as well as space. So it is a both function of time and space. Earlier we have only a function of time, so we can directly integrate this, but here it is not the case. So we will use some what we call as order of magnitude. Order of magnitude. So what our order of magnitude says is, so suppose the equation is like this: rho del u by del t is equal to mu del 2 u by del y square. So if I do the order of magnitude, so order of magnitude says that what is the maximum velocity that you can possess is u infinity. Suppose this plate is moved as u infinity. Now, what is the time scale? So I am saying such some time ts is so order of magnitude. What it means is, so suppose a equal to b. So whatever be the order of a is equal to order of b. That is the meaning of a is equal to b. Because suppose this is 1000, this cannot be 10 because this will not be equal. Now here we have u infinity into del y square. So here what is the y? Suppose this is we called it y square. So what it means is at what till what point? So at some ts time till what y the velocity is felt. So this is what is called a diffusion term because it is diffusing the velocity, and this is the transient term or temporal term. So if I simply solve, this term will go out. So why I write y square? Here I write u infinity, here I write y square. So it comes in this way: del of del y of del u by del y. So del u by del y is u infinity by y, and this again del of del y. So this is again 1 by y. So it is equal to u infinity by y square. In this way it is coming. So if I simply solve this, you will get y is order of magnitude of under root of mu into ts. That means as the time evolve, your y, that means till what point the velocity this velocity is felt will increase because the last layer has gained some velocity. This is the transfer of momentum. That means if I say, so this is your velocity, this is your y. So it will be like initially only this much y, or I should make it more steeper way. In this is June infinity. At initial time, suppose only this much y has felt. With time, it will increase and it will go on increasing in this way. So this is at time at t increases your the time for which the distance till which the disturbance has been propagated has increased. Okay, so this is how the time evolves. So as you can see, your velocity is a function of time and as well as space. You cannot simply solve this equation. You need to use it as a you need to use similarity variable. So I don't know whether you get this or not, but we can define a eta, which is a function of space as well as time. So this is a combined function of space and time, and we will try to induce this velocity in terms of eta. So du by dt is equal to, so this is a only function of space and this is only function of time. So y into g prime of t into del eta by del t. Because if you say suppose you integrate, so it will be del g of del t. So it is uh, or it should write del g by del eta into del eta by del t. So it is a differentiation by like integrate differentiation rule. Now del u by del y is equal to, so y would go away. So it is del u by del eta into del eta by just wait, I should write it a more clear way. That's difficult to understand. So if I'm saying del u by del t, it is del u by del eta into del eta by del t. So del u by del eta into eta is this function. So it will be y into g of function of t. Similarly, del u by del y that is equal to del u by del eta into del eta by del y. So del u by del eta into, if I differentiate it, it is only g. So if you take the again the derivative, it is del 2 u by del eta square into g square. So if we can simply put in the this equation, it will be rho del u by del eta into y into g is equal to del 2 u by del eta square into g square. It is g prime. Okay, this is g prime. So del 2 u by del eta square divided by del u by del eta, and y we can replace it as eta by g, because here we can shift y as equal to eta by g. So it is 1 by eta is equal to this is mu. So mu g cube divided by I should write another direction. It is g prime by g cube. So this eta and this g. So g is function of only time, and this is function of eta is a different variable. So each should be a constant value. Then only this can be possible that both the variable are separated. So if you simply solve this, mu g prime by g cube is equal to some constant, or mu into dg by dt is equal to some g into g cube, or I think this is 1 by nu. It should be 1 by nu, or this is c nu g cube. This is some constant, and dg by g cube is equal to nu c into dt, or g is equal to under root of minus mu c t plus some c1. So if you see this, so what is the condition? So this is a function of time. So if I say at t, uh, what you say, since theta is equal to y into some function of t, at t tends to 0, y tends to 0, because at when at the starting there is no penetration. That means eta by y is equal to g of t. So if y tends to 0, this term tends to infinity. Therefore, g of t is tends to infinity. So if I say, so it is g raised to the power minus 2. It is like this because g cube will come in this way, or I should write in this way. G raised to the power minus 2 is equal to under nu ct plus c1. Now, since if this is possible, therefore at t then t is equal to 0, this term will go to 0. This term is 1 by g square. If this term will go to infinity, this whole term will go to 0. Therefore, c1 is equal to 0. That means g raised to the power minus 2 is equal to under root nu ct, or G is equal to 1 by under root of mu Ct, and it will come with negative sign. This will come with a negative sign. Now, what is the possible value of C? So, since it is a square root, C can be only negative values because this should come as a positive term. So, if I suppose I am taking C is equal to 2, so what happens is, or I should say 4. Let me take as 2. So, G is equal to, it will be 2 at the bottom. So, this will 2 multiply here, and G is equal to G is the order of under root of mu t. So earlier you had seen that we had obtained a y that is the order of mu into t from just the order of magnitude analysis from the similarity variable. The same thing is coming at G is the order of 1 by under root of t. That means your G as the time progresses, this term will change. So suppose now another term is remain. So 1 by n del 2 u by del eta square divided by del u by del eta is equal to, suppose I am saying minus 2 because I had taken c is equal to minus 2. Therefore, del 2 u by del eta square plus 2u del u by del eta is equal to 0. So this is your another term. Now, what you will do is you just simply integrate. So let del u by del eta is equal to some function f. So it is del f by del f by del eta plus 2 mu del f by del eta is equal to 0, or sorry, this f. So if you just integrate, it is equal to integration of 0 to in eta. No, no, it is, if you just integrate, it is f is equal to e raised to the power um, minus 2 mu eta plus some constant. Now, since del u by del eta is equal to f, it will be f is equal to e raised to the power. So it is integration of 0 to eta e raised to the power minus 2 mu eta. So some constant c1 plus c2. So this is your velocity profile. So in this is your error function. So you can simply look in the error function, but in this way you can solve. But here you see the complexity will arise because you don't have a separate, you cannot separate u as a function of, because u has velocity as well as space term. So we need some term that will replace. So we called it as a similarity variable. Okay, this similarity variable will do this. Will do this thing. Now, in this flow between parallel plates, so in flow between parallel plates, suppose your velocity profile is known. Just one thing has been missed, so I will tell you. So if I say, suppose this is y equal to 0, y equal to h, and y equal to h, and y equal to minus h, and your velocity profile is something like this. So u is equal to minus 1 by 2 mu dp by dx into h square minus y square. So this is your capital H. Okay. So y equal to minus h, y equal to plus h. Now you may need to find what is the shear stress. So as you can see, shear stress is equal to tau is equal to mu du by dy. Okay. So if I just derivate this velocity profile, so du by dy is equal to minus 1 by 2 mu dp by dx into minus 2y. So this term will go away and this 2 will go away. So it is 1 by mu dp by dx into y. Now this gradient should be equal to at minus h. Because why at minus h? Because at this only the shear stress is felt because of the no slip boundary condition. If I put minus h, it would be minus 1 by mu dp by dx into h. This is the, if I multiply with mu, it will be the shear stress. So if I just take the mu on the right hand side, it will be uh, tau at minus h. So what this negative signs means? Negative sign means. So obviously dp by dx is less than 0. So this term is less than 0. That means this is a positive quantity. What it means is in on your fluid. So if your fluid is like this, so the gradient at this point is positive. This is the meaning of this shear stress. Or what it means is this plate this plate is trying to head or this is a shear stress on fluid. Now from so this whole term is a positive quantity. Now from Newton's third law, you need to apply the force in the negative x direction to hold the plate because the fluid is trying to move the plate. Therefore, the force you need to apply it should be in negative x direction. Why that is coming? Because this whole term is positive quantity. That means the fluid is trying to drag the plate in the right side direction, but you need to hold the plate in the backward direction. Now, what happens in the top plate? So if I put top y is equal to h, du by dy is equal to at h is equal to uh, so it is 1 by mu dp by dx into h. So if I just say tau at h is equal to 1 by mu dp by dx into h. So if you say this term is negative quantity, that means the shear stress by the fluid on the plate is in the negative y direction, and you need to hold the plate in the right side direction to make the plate stationary. This is the meaning of what is the meaning of the shear stress at the wall. Now, there is a relation that I already told you that U max is equal to 3 by 2 of U bar. So this is the maximum velocity that is happens at the center. That is equal to, this is the mean velocity, and it is 1.5 times the mean velocity. Now another thing is you need to find what is the coefficient of this is called skin friction coefficient. Skin friction coefficient. So what it says is CF is equal to tau wall by half rho U bar square. So this is what is called as skin friction coefficient. So here tau wall is dp by dx into h. So I am taking the mod value. So it is mod value. Okay. dp by dx into h. Now, second thing is, uh, you know that u bar is equal to, so the thing is u bar is equal to, you can simply find it is dp by dx into h square. Now you can substitute dp by dx from here and you will get tau wall in terms of u bar. So dp by dx into h, it is equal to, so minus 1 by 3 mu tau wall into h. Sorry, u bar equal to. Now we can simply put tau wall mod by half of rho into u bar square. It is 1 by 9 mu square tau wall square into h square. Or what I should do is, it is tau wall by half rho u square. Okay, or I should write in the velocity term, tau wall is equal to 3 mu u bar divided by h. So I should substitute the other ways because we need the velocity component, not the shear stress component. Okay, so it is 3 mu u bar divided by h into half rho u bar square. So what will it will come as 6 mu divided by rho h u bar. So rho h u bar by mu is equal to Reynolds number. And here h is 2h because the height is 2h. So it is 6 by Reynolds number of 2h, and that is equal to 12 because we need 2h and we need to multiply it also by 2. So this is your skin friction coefficient, that is equal to 12 by REH. Now, uh, so now one question is, so we have one question that says that water is water is flowing at 20 degrees Celsius in between in two-dimensional channel flow or two-dimensional channel, and the distance between two is 1.5 mm. Your average velocity is given 2 meter per second. You need to find what is the maximum velocity. Okay, what is the maximum velocity? What is the pressure drop? And what is wall shearing stress? Wall shearing stress. And it is given that mu of water is equal to 0.00101 kg meter per second. So suppose this is your channel. It says that u bar is equal to 2 meter per second. Now, we from the our basic calculation, we say that u max is equal to 3 by 2 times of u bar. So that means 3 by 2 into 2, that is equal to 3 meter per second. So one thing is u max, the maximum velocity is 3 meter per second. Second thing is, if you just simply put uh, this equation, u bar is equal to, if you simply put u bar is equal to minus 1 by 3 mu dp by dx into h square. So uh, this h is half the channel width. So if you simply put u bar is given 2 is equal to minus 1 by 3 mu dp by dx. This is the pressure gradient we need to find into h square. So it is 1.5 divided by 2 into 10 raised to the power minus 3 whole square. So if you say the dp by dx is minus 10800 Newton per meter square per meter or Pascal per meter. That means nearly uh, it is that nearly around 1 bar uh, pressure has been dropped over a 1 meter pipe. Okay. Now the third question is, what is the wall shearing stress? So wall shearing stress is tau wall is equal to dp by dx into h. So h is half channel width. So if you just simply put 10800 into h, what is that we called as a half channel, that is 1.5 divided by 2 into 10 raised to the power minus 3, you will get 8.08 Newton per meter square. This is the tau wall. Okay, this is what is happening. This is wall shearing stress that is happening because, or simply we can solve from the mu also, but because we have a velocity profile, or this is just wall shearing stress. Now, uh, just wait for 1 minute. Okay. Uh, okay. Now, this is like the one question. Now, now this another question that I told you. What we will try to look at. This would be probably the last question. This is U is equal to 0.3 meter per second. A fluid is flowing. Uh, uh, no, not it's not like that. So this bottom plate is moving in the negative y direction at 0.3 meter per second. This is the spacing that is 3 mm, and you have mu is equal to 4.7 to 10 raised to the power minus 4 Newton second per meter square. Now the second the part is, as you know, this can be solved as mu del 2 u by del y square is equal to dp by dx. And the basic thing that you need to think is what is the pressure gradient for which no flow is occurring. No flow is occurring. That means since it has induced the velocity, what is the pressure gradient that on an average cross section no flow will occur. So that means there would be a circulation. So if I'd say it would be like that. So here we have this type of circulation, here we have this type of circulation, and in the net we don't have any type of any flow that is happening in any cross section. That is, although the flow is happening, but no net flow is happening. So if you simply solve, you will get 1 by 2 mu dp by dx into y square plus c1y plus c2. Now at y is equal to 0, u is equal to minus u, that is 0.3 meter per second. If you put that in, c2 is equal to minus u. And at which is y equal to 0, it is y equal to b. At y is equal to b, you have u is equal to 0. Therefore, the final velocity component is u is equal to 1 by 2 mu dp by dx y square minus by plus u into, so this is capital U, y by b minus 1. So this is the velocity profile. Now we don't want any flow over any net flow over the cross section. So what we will do is we will find q, that is integral of u dy divided by 1 by b. No, this is average velocity. Okay. So it is u dy. So this is the flow per unit width. This is flow per unit width from 0 to b. We will integrate this and we will put this equal to 0. That is, if we made integration over the whole channel, there would be no any flow. So if we just make this 1 by 2 mu dp by dx into y cube by 3 minus by square by 2 plus u into y square by b 2b square minus y, and this whole has a limit of 0 to b, and that is equal to 0. So if you simply put, you will get dp by dx is equal to minus 6 u mu by b square So if you put that thing, you will get 94 minus 94.0 Newton per meter square per meter. So that should be the pressure gradient that should exist so that no net flow will occur inside the channel since it will form a circulation. Okay. So the same thing can be derived. Same thing can be derived for the for the cylindrical coordinate also, like in the pipe flow. The same thing can be derived, and you will get a velocity profile that is v is equal to minus r square by 4 mu del p by del z 1 minus r square by r square. So the same thing can be derived, and you will get a velocity profile. The assumption would be same: a steady state, fully developed, fully developed, no body force, okay, and no slip boundary condition will be valid. So if you solve this, you will get this velocity profile. V average for the cylinder is, so if you say V average for this cylinder is, um, it is minus r square by 8 mu del p by del z. V max is, I think, minus r square by 4 mu del p by del z. That means V max is equal to 2 times of V average. That is one thing that is there. Now, second thing is tau wall is equal to minus mu del u by del. So suppose this is your r coordinate, this is your z coordinate. Del u by del r at r is equal to 0, or r is equal to 0 is this one. Actually, it is r equal to 0. This is r equal to r naught. So it is del u by del r at r is equal to r naught. So if you just simply solve, you will get a shear stress, and here the spin friction coefficient is 16 by Re. So if you solve 16 by Re, you will, that means the spin friction coefficient depends on only the Reynolds number for the laminar flow. So that is Re is equal to rho v d by mu. So this is your inertia force, and this is your viscous force. So if you have all the equations in your hand, you can simply solve and you will get the pressure gradient, the velocity profile, and everything. So on experimental basis, what people used to do is just they simply so in the long channel, what they do, they simply connect a U2 manometer. So they will get a pressure gradient over a length x. So suppose this is length x. So they will get delta P from the reading of manometer. From manometer, they know what is the x in between the manometer is connected. So they will do as delta P by delta x is equal to dP by dx. And they will simply put in the equation and they will get what is the average velocity that is flowing, what is the maximum velocity that is flowing, what is the shear stress. So one thing, why we need this pressure gradient? What is the importance of this pressure gradient? So suppose I need to drive this flow. How I will produce this pressure gradient that there we have a higher pressure, there we have a lower pressure. So what you will do is you will connect a pump in between. So suppose I drive the flow using a pump. So what is the power of pump? So power rating is uh, is calculated from delta P. So how it is calculated? So power rating of pump is equal to delta P into flow rate. So this is divided by the efficiency of pump. So this is the power rating of the pump that is we have to calculate. So if you know delta P and you know the flow rate, you can directly calculate what is the power rating that is required. power rating that is required. Okay, I hope you got this for today's class. So we will meet next time, and then we will solve like another problems. So this will help you to solve the new assignment that is given. So I like the assignment you had seen. It's from the exact solution of Navier-Stokes equations and Euler equation impact object. So you can solve that thing. Uh, okay. Thank you.
Thank you, sir.